Hey guys, welcome back to another RASK Maths video, and in this video I'm going to be showing you guys how you can solve almost any polynomial which you'll be given using rational root theorem. So rational root theorem is pretty simple, but it's super powerful as well. So it basically states that if you have a polynomial, let's just call this p of x is equal to, let's call this a of x to the n plus b of x to the n minus 1, you know what I mean, because it could be like x4 to the x cubed, things like that. Carrying on all the way up to just something like, let's say, c of x plus d. Let's just say that. So obviously a common problem which you're going to have to solve is trying to find the roots of this polynomial. So usually this is easy when you have it degree 1, degree 2, and those things, because you can just either rearrange and solve, or you can just use quadratic formula. But it starts to get a bit more challenging when you get to cubic, and then it gets a lot more challenging as you go higher up. So this is going to offer us a very simple way to solve it. Basically what it says is if you need to find all of the factors of a, or just the highest degree polynomial, so factors of highest degree x term, I'll just call it that, over, and you also need to find, let's call these factors, let's just call these f1, and we'll call the factors of lowest slash constant term, and we need to find both of these terms factors. So this is the factors of a and the factors of d in our case. And basically what it states is all rational, or all possible rational solutions will be, there will be plus or minus the factors of the lowest constant term over the factors of the highest degree x term, just like that. And this will give us all of the possible rational solutions. Obviously, if this polynomial has 0 rational solutions, then it's not going to give you any of them. But this is just stating that you can find some of them using this. So now I'm going to show you guys how to use it in practice, and some high degree polynomials which we're going to solve using this. So first of all, let's start with a polynomial, let's say x cubed minus 7x plus 6. Let's just say that, okay? So, so first of all, we need to get the factors of the highest degree, which in this case is just 1. So factors of 1 is literally just 1, just like that. And now we need the factors of the lowest term, so factors of 6, well, we got 1 and 6, and we've also got 2 and 3, just like that. So we've got all possible rational solutions. I think it's Q for rational, though might be wrong, but yeah, so all possible rational solutions, and we've got plus or minus 1, 6, 2, 3 over 1. So what that comes out to is our possible solutions are going to be 1, 6, 2, 3, and then the negative versions of all of those, just like that. So obviously you still need to try all of these, but this narrows down your search so much, because you might have to otherwise test out every single number, but now you know that it can only be these if it's going to be rational. So now we can just start testing, and since this is a cubic, all we need to do is find one solution, and we can just use polynomial long division or synthetic division, and to reduce it to a quadratic, which you can just use a formula. So from this, if we simply plug 1 into all of these, you'll actually see 1 is a solution. I should actually make this equal to 0, so it's actually an equation. But yeah, so if you plug 1 into all of these, you'll see 1 is a solution, so we can tick 1. If you plug 6 in, you will see that it's actually not a solution. But if you plug 2 in, you'll see that 2 is also a solution. So that also works. And if you just carry on like this, keep on going, you'll see 3 isn't a solution, but what you will see is -3 actually is a solution. -27 plus 21 plus 6 is 0. So these are actually our 3 solutions. We just got them really easily, all rational, so we were able to get them super simply. But let's say we only had the x term, just like this. Well, what we could do is, using this, we know x equals 1 is a factor. And we could use synthetic division, which I will use, but you could also use the fact that x minus 1 is a factor and then use long division. That's just a bit longer. And if you haven't watched my video on synthetic division, then you should probably go and watch it. I just uploaded it recently. So yeah, let's use synthetic division to calculate the resulting quadratic when you divide this by the factor. So we've got 1, 0, -6, -7, and 6 as the coefficients of our cubic. And we can just put 1 into here and carry that down. And now we just start using synthetic division. You can just see how fast it is, able to get our resultant quadratic just like this, and we get x squared plus x minus 6 is equal to 0. And then of course from here you can just use quadratic formula, or you can just factorize. So by doing that, let's just factorize this. You're going to get x plus 3, x minus 2, and then you'll get x equals 2 and minus 3, which were our other solutions which we found earlier. So yeah, that was one example, pretty simple example, because 1 was a solution, and it's always nice when 1's a solution because you can always just do the coefficient test and just check if the coefficients add up to 0, and if that's true, then 1 is a solution. But yeah, let's go on to a slightly more complicated situation, just so I can show you the true power of this. So let's rule that off. And we're going to have another example. We're trying to solve the equation 3x minus 5x squared plus 5x minus 2 is equal to 0. So this is slightly more complicated. I don't think you'd be able to just look at this and immediately give me a solution. Like 1 isn't a solution. If we do that, it's actually going to give us 1. So that's not a solution. So let's find all the factors. First of all, we need to find the factors of 3 for the leading term. And that's going to just be 1 and 3, since 3 is a prime number. Similarly, for 2, we're just going to get factors of 2. And that is just going to be 1 and 2 again, since 2 is a prime number as well. You might be wondering why I just ignored the minus sign, but it's because rational root theorem includes the plus or minus anyway, so the minus sign is not really going to do anything. So anyways, now you get all possible rational solutions, and we're going to get plus or minus 1 or 2 over 1, 3, which comes out to giving us plus, so we're going to get 1, 1/3, 2, and 2/3 as our possible candidates, and we also have the negative versions of all of those, just like that. And you can see again, we've got 8 possible candidates, so it's quite a few, but it's better than, again, having to put in like random numbers and just getting. Also, you'll notice that we've got fractions, which usually people just don't try, because if you're going to start including fractions, then it's going to take a much longer time. So we can start putting these in. 1 already doesn't work, so we knew that. If you put 1/3 in, you'll actually see that it doesn't work, so that is another one which doesn't work. Similarly, if you put in all of these, of course I already put them in, but if you put them in yourself, it doesn't take too long. You can just put it in with a calculator, and you'll actually see that 2/3 does in fact work. So that's great, and you can just, now you know that x equals 2/3 is a solution. So of course we can use our rational root synthetic division, but you'll notice that if you divide this by the factor x minus 2/3, this actually gives you a quadratic which has no real solutions. Discriminant is smaller than 0. So there's no real solutions, which leaves only 2/3 as the only solution to this cubic, which makes sense. If you look at its graph, it's actually a bit like this. So that would be 2/3. Anyways, those were two cubics, and the thing about rational root theorem is that it's really useful for cubics because they're just one step away from quadratic. So once you find one solution, you can reduce the cubic down to a quadratic and then solve it using quadratic formula. So you can use this though for any order polynomial. So I'm going to show you guys one more example, and let's do it on the polynomial of degree 4. So let's have 2x to the 4 plus x cubed minus 13x squared and minus 6x plus 6. There is our quartic polynomial. So let's start off with the same process. We want factors of 2. And it's always great when we get a prime number because we're going to have little factors. You want as little factors as possible because you're going to have to combine all of them. So if you have too many factors, then it's going to be difficult to have a reasonable amount of possible candidates. But anyways, let's go to factors of 6 now. And you'll see that is, that's in fact going to be 1 and 6, 2 and 3. Those are our factors of 6. So now we can get possible rational solutions. And notice how I keep saying rational because when you go to higher order things, even in quadratics, you might have some solutions which aren't rational, like square root of 2, things like that, square roots, cube roots, those aren't rational. So you can't actually get them using rational root theorem, which is why it can't be used to solve absolutely everything. But this still offers like a really good tool because most cubics which you encounter or most polynomials will actually have rational solutions. So we've got plus or minus 1, 2 over 1, 6, 2, 3. And that comes out to giving us, I'm not going to write out everything, but you get plus or minus, and then if you put everything over each other, you get 1, 2, and 1/6, 2/6, which is just 1/3, 1/2, and 1. When you put 2 over 2, which you've already got, so we can get rid of that. And finally 1/3 and 2/3. We've already got 1/3, so we've just got 2/3 now. So there are now new candidates. And if you put these in, you will notice that, just did the same arrow twice. But yeah, if you put all of these in, you'll notice that you actually get -1 as a solid solution. And you can actually verify that if you put -1. So you're going to get 2 minus 1 plus 2 minus 1 minus 12 plus 6, which is 0. So we can conclude from this that x equals -1 is a solution. And then obviously we can just use synthetic division again to reduce this even further to give us a cubic, which we may be able to solve again using a rational root theorem. But yeah, you can see how this is super useful in reducing polynomials to lower orders until it's that good quadratic, because then you can just use the easy quadratic formula. So this is great for cubics and higher order ones, but yeah, this is especially good for cubics because they're one step away from quadratic. So thanks for watching, and that was how you use rational root theorem in maths. See you guys in a future video. Bye.